you know that it goes like this, right? So hopefully, right? So what happens as the X value gets bigger, right? Positive, it starts spitting out positive numbers, and then it goes to 0 and then starts spitting out negative numbers. We have the same thing happening in reverse now. So as the Y gets, as you start plugging in Y's, right? Positive, that's kind of like what we were doing with the X's here. The outputs are positive first, and positive means to the right, on right of the Y-axis. So you start drawing this, then you go back to 0, then now you have negative values, and then you go back. So that is that one. Does that help? Was it Cameron? Did you ask? Yeah.
I figured it out like as soon as I saw
okay.
The unit circle.
Okay. And then let's say the blue one, of course, would then have to be this one. That's your cosine function. So it starts out at 1. And as you plug in positive values, it starts to go down, then back up, right? So Y equals 0, where's that? Y equals 0. That's the x-axis, right? And Y equals 2 pi is this one up here. We want the area of this entire region, everything together. So does someone see what we're going to need to do? Or do y'all see what the
separately?
Like we break it into different parts and do the horizontal rectangles.
Yeah,
and then
we have to do horizontals. We have to do horizontal rectangles because if we try and do vertical rectangles, there's problem. We have issues. Like right in here, if I try a vertical rectangle, that's a problem. Try and do a vertical rectangle here, it's a problem. If I try and do a vertical rectangle here, it's a problem. So I can't do vertical. I have to do horizontal. But the issue is that, you know, in the bottom region, right, in this region, the one on the right is the blue and the one on the left is the red. But then when you get to this region, they switch places. And then when you get to this region, they switch again, right? Which means we're going to have to break this into 3 integrals. Yes?
Mhm.
No, I was going to suggest that maybe we need to do individual integrals. Like there's one cycle on each, and we know if we split it by half, that will be the area on each case, and then we can deduct it. Is it too much? Is it even right?
Yeah, I think you're overthinking it. You want to just look at it as you've got 3 separate regions, region 1, region 2, and region 3, and we can do an integral for each one. For each one of those, we have a right function and a left function, and you still need to figure out the limits of integration. So you still need to figure out like where to start and stop on this one. And then on the next one, you need to figure out where you're going to start and stop your y here. And on the last one, where you're going to start and stop. Does that make sense? So you still have to figure out where these curves intersect each other. Now you can tell from my picture, right? You can tell where they start and stop, but that's cheating because you're using my picture. So what we would really have to do is set sine y equal to cosine y, right? Be setting these two equal to each other to find the intersections. And now we have to solve this trig equation, which is a pre-cal problem. So if it were me solving this, what I would do is just divide both sides. Well, there's so many different ways to do this. How about I do it this way? If you think about the unit circle, what we're saying is where is the sine and cosine the same, right? Where are they equal? So at what angles are the x and y coordinates identical?
45 degrees.
45 degrees, which is pi over 4. And
3.
down here, that's 5 pi over 4. That's where your x's and y's match, right? Because this is the root 2 over 2, root 2 over 2. And this one down here is negative root 2 over 2, negative root 2 over 2. Now, there's an infinite number of answers because, you know, you could keep swinging around and doing more rotations and stuff, but we're only looking between 0 and 2 pi, right? That was what was given to us. So that's how I could conclude that's 5 pi over 4 5 pi over 4 and pi over 4. So let's do the first integral. And maybe I should label these just so it'll help us. The blue curve is the cosine y, right? And the red curve is the sine y. So for the first integral, we are going to have the integral from where to where?
0 to 2 pi.
0 to pi over 4. And then it's going to be the right one, cosine
The
y,
blue.
minus the left one, dy. That should give me the area of region 1, right? Then I need to add to that a new integral, which goes from pi over 4 up to 5 pi over 4. This time it's flipped. It's the sine is the one on the right minus the cosine is on the left, dy. That should take care of my second region. And then the third region goes from 5 pi over 4 to 2 pi. And that goes back to the original one, cosine y minus sine y, dy. So you have to do all three of them. And we do not have any symmetry here. In other words, we can't just find one of these and then triple the answer, right? Because these regions don't look the same. It'd be nice if they were all equal and then I could just find one and multiply times 3, but can't do it here. So each one of these is going to give us a different answer. We add them up and we have our result. Okay. Understood? All right. I think that we should move on to 7.2.
Is it possible to get a copy of this work that you just did?
At the end, I'll save all this as a PDF and I'll send it out as an email. Just
Okay.
remind me, okay? Remind me, please.
Sure.
So in this case, we need to find the antiderivative of all of these.
Yeah. And the
then-
antiderivatives are straightforward, right? Antiderivative cosine is just going to be sine, antiderivative, well, sine of y. Antiderivative of negative sine y is cosine y. And then you plug in your endpoint. So
So
like if I,
I was
did just-
about to say that it's hard because I thought that was a multiplication sign. I forgot that
Yeah.
when there's an addition, we can just solve them separately.
yeah, so this would be the first one. You have to do this. Antiderivative, and then you plug in pi over 4, get an answer, plug in 0, get an answer, subtract. That'd be the area of the first one. And you do that for each one of these.
Understood.
Now, real quick, how did we determine the numbers? You said just by looking at this, the
So
circle?
the pi over 4 and 5 pi over 4,
Yeah,
we got those from setting the two curves equal to one another. Sine y equals cosine y, and then using the unit circle to say, well, when is sine equal to cosine? At what angles? So sine and cosine are the x and y coordinates,
mhm.
right? Cosine is the x coordinate, sine is the y coordinate. So where on the unit circle are the x and y coordinates identical?
So
And
we
that
say at
happens
45, right?
Here. At 45 degrees or pi over 4, or 215 degrees, which is 5 pi over 4.
Okay, so it's from 0 to pi over 4, and then from pi over 4 to 5 pi over 4.
And then 5 pi over 4 to 2 pi.
Okay,
And we're only looking between 0 and 2 pi because they gave us, right? They gave us 0 to 2 pi here. They
Mhm.
gave us that. Okay.
got it.
All right. So you should be able to at least go after the homework for this section. You know, go through and look at the first 19. It's all going to come down to, can you draw them? If you can draw the graphs, can you determine if you're going to be doing vertical rectangles or horizontal rectangles? That's what it's going to come down to. All right. And then it's either top minus bottom or left minus right. You might have to find some intersection points, which might mean you need to do some algebra or some sort of trig equation or something like that. All right, we're moving on. All right, we're about to start a really, really nice section, 7.2. Volumes. These are also called solids of revolution. Solids of revolution. I always just want to like put my fist up, you know, it's revolution. It isn't that exciting though. Okay, solids of revolution. So before we can start, I need to remind you about some things, some geometry. So if we have a rectangular box, which is mathematically known as a parallelepiped, that's the technical name for a rectangular box. The volume of it is how much stuff it holds, right? Like if you were to pour something into it, how much volume it contains. The volume formula is just length times width times height. So if you know all three sides, then we can find the volume of that by just multiplying length times width times height. Now, if we have a right cylinder, that is just like your basic good old cylinder, like a beer can or soda can, then the volume of this is pi r squared times h, where h is the height of the can. And where does the pi r squared come from? That looks familiar. Pi r
The
squared.
radius from circle.
That's the area of that, isn't it? The area of that is pi r squared. If you know that the radius of the can is r, right? Then all you're doing to find the volume is you're finding the area of the top and then multiplying by how deep it is. Okay, that's how you find the volume of a right cylinder. Now, the volume of what's called a washer, I'll get to the shell in a minute. The volume of a washer, the way this works, consider the problem we just did up there. Oh, shit. Let me see if I can undo that. Yay, I did. All right, so imagine we have a cylinder that has a radius, I'm going to call that radius r out, and a height of h. But then I have a smaller cylinder inside of it that I'm going to cut out of this. So it's almost like I'm going to drill a hole down through the middle of this can. The can was solid, but now I'm going to drill a hole. Well, if this cylinder on the inside has a radius of r in, then the volume of this thing should be the volume pi r out squared times h. That's basically pi r squared times h. That's using the outer radius, finding the volume of the whole thing, and then subtracting from it the volume of the inside piece. Does that make sense to everyone? Yes? Since these both have a pi and these both have an h, I can factor the pi out front and I can put the h out back. I could put the h in front too, but I'm putting it in the back for a reason, all right? So do you all agree with this formula? If you have a washer is basically an outer radius and an inner radius, then the volume of that should be pi times the outer radius squared minus the inner radius squared, all of that times h. Any questions on that? Okay. All right, I need to bring up another file. I thought I had it ready, but I don't. Where are you? Where is it? Crap. There it is. It's in my presentation. I thought it was on a separate file, but it's in here. All right, so look, what we have here is nothing new, right? That's nothing new. We have the area between two functions. These are both functions of x, agreed? What we want to do now is something very strange. We want to imagine that this two-dimensional picture is in three-dimensional space, which means we want to kind of see that it's living in 3D. Okay? Then we want to imagine taking this entire region and rotating it around the x-axis. So we want to take this and we want to rotate it around the x-axis. And as it rotates through space, it kind of leaves a trace behind it and it's creating a solid. Do y'all see that? Now I'm gonna make this thing somewhat transparent so we can see through it. Okay. This solid that we have here, we can see through it, right? This solid has a volume to it. And what we want to know is what is the volume of that solid? Understand the geometry, understand the question. Yeah? For those of you who are interested, everything that you're seeing here, this animation that I'm doing, is all done in a program called Wolfram Mathematica. Now, everyone's familiar with Wolfram Alpha. That's the website you go to. But Wolfram is a company that's had math software for years and years. When I was in school as a math major, I actually bought the student version of Wolfram Mathematica 1.4, I think was the version that they were on. You're looking at version 10.0. I think they're on 12 now. So the way Wolfram Mathematica works is that it's essentially C++. So there's all my code that I wrote to make all that happen, okay? It's a lot of built-in functions. It's nothing fancy. As long as you know what the functions do, you just got to get the syntax right. So this was all done with just coding up in Mathematica. And I created this thing. So pretty cool. If you're interested in that sort of thing, I'm happy to share any of my code with you. All right, I've got files I can just send them to you. Okay, so you got this, right? We're good. Understand the geometry. Let's pull this thing back. Let's pull it back here. Get back to the 2D and be like, well, how are we going to go from that to the volume, right? Like, how do we do that? So here's what we're going to do. We're going to go back to the original picture we had. If we've got two functions of x, we can take this rectangle, right? Now, we had come up with a formula for the area of that rectangle. But what I want you to now kind of visualize is if you took just this rectangle, okay, here it is, and here's your axis, the x-axis. We're calling this the axis of rotation. If you were to swing this rectangle around the x-axis, you would create this shape. Do y'all see that shape from just wrapping this around? It's important that you see that, because if you don't see that, it's take that, swing it all the way around. Here's your axis of rotation right here. You're rotating around there. You're going to have this hollowed out washer, right? You're going to have a washer. Now it's a washer sideways. It's that cylinder inside the cylinder, but it's all turned sideways. And we actually know what the volume of that washer would be. It would be pi times the outer radius squared minus the inner radius squared times the height. That's the formula from the previous slide, right? So let's talk about this. Do we know how wide it is, or do we know the height of it? How tall is the cylinder? Well, that's the width of the rectangle now, isn't it? It's how wide the rectangle is how tall this is. Yes? Because you're looking at it sideways, right? So this is, it's kind of like we have this.
I guess in that case,
This
the
is our
height will
height.
be dx.
It'll be dx, because dx, the width of the rectangle, right, has always been dx for us. So that's going to maintain dx as the width or the height of our washer, right? Then we need to know what the outer radius is. The outer radius is the distance. Listen to what I'm saying. The outer radius is the distance from this axis of rotation to the outer edge of the rectangle, isn't it? Again, look at it sideways. Or let me, I don't know. Do y'all see it or not? I mean, maybe I can do this. When we had this cylinder, we had an outer radius, and then we had an inner radius. We're doing that same picture, but sideways. So the outer radius should be the distance from the center to the outside of this, right? To the outside, which would be to that edge. And isn't that distance always going to be the function's value there? The function f's value? Y'all see that? This height from here to here is actually corresponds to the outer radius. Now, if you move to a different rectangle, doesn't that radius change? Doesn't it change? Yes. Both the radius here and the inner radius, which would be the bottom of this, would be your inner radius because that's this edge right here from here to here. Do y'all follow that?
So basically, we are not going to take the area like we were doing it between the top and the bottom curve, and
That's right.
we're just gonna rotate the cylinder.
Yeah. So I said last class that it was so important for everyone to understand what this integral meant geometrically. We said geometrically, this just meant, this is the beginning of class last time, I said this just meant that this was the height of our rectangle. This was the width of it. And the integral meant we wanted to add up an infinite number of them. And when you do height times width, you get an area. So we wanted to add up a bunch of areas, which gave us a total area. Here, we're not talking about area. We're talking about volume of something. It's the volume of something abstract that we can't even really see. We're just saying, if we were to rotate it, what would we get? So I'm taking one rectangle, I'm wrapping it around, and what I'm getting is that shape. Now, what is the volume? What is the volume of one washer? Okay, so what would the volume of this one washer right here be? Pi, right? Pi times the outer radius squared. What's the outer radius?
F of x.
The f of
F of x. So I'm going to write f of x squared minus the inner radius squared. What's the inner radius?
g of x.
G of x. So g of x squared, and then times the height. So I'm using this pi r out squared minus r in squared, which everyone told me they agreed that this formula was right. Okay, so what was the height for us?
Dx. The
dx,
derivative.
right? Dx.
So the derivative is in terms of what? Like we're gonna take the derivative of f of x.
We're not taking the derivative of anything. We're not taking derivative of anything. We are saying that dx is the width of the rectangle, right? Which corresponds to the height of this washer. Dx is just a number.
So in terms of dx, do we need to find out by taking out the derivative of something, or is this a
No.
number?
No, this is, look, I'm trying to build the formula. Trying to build the formula. That's what I'm trying to do. Just like we did last class, we tried to find a formula for the area of one of those, right?
Mhm.
One rectangle. And then we said, let's add them all up. And so we brought the integral in. What we found here is the formula for the volume of one washer. Now, what do we want to do with it?
Uh,
Volume
Add them
of
all up, right? All the washers, all the possible washers in there. So how am I going to add up an infinite number of things?
integral.
I'm going to integrate this from A to B, because A to B is still where we're going to be sliding. So we're still sliding rectangles, right? We're sliding rectangles, but each time we move across, we're wrapping it around and creating a washer. Move it a little more, wrap it around, create a washer. Move it a little, wrap, create a washer. And what you do is you get all this, the whole volume. I do have another animation. Hold on. I know I have another one. Let me just see where it is.
So essentially what we
Yeah,
can say, it could be a washer or it could be the volume on a, call it a toilet paper, the whole thing, the outside minus the inside,
right.
correct?
Each washer is like a roll of toilet paper, except it's infinitesimally thin. Okay, so here's another animation. This might help, okay?
That was not a good example, but it worked.
Okay, so here's another example. Now, this is, again, is three-dimensional. Just imagine taking that rectangle and wrapping just that rectangle, just a single rectangle around the x-axis, okay? Now there, we're not creating a washer, we're creating more of like a disc because it doesn't have a hole in the center, right? But we're trying to do a bunch of these. We're trying to vary. When we integrate, we're moving across, we're moving left and right here, starting down here. As we move across each one of those, we're adding all these up, right? But we're making these very, very, I mean, we could start out being really wide, but we're trying to get really narrow ones. And so imagine all of them, like imagine a bunch of them there, right? Like,
Could we
that's what
say that depending on the function, it's the silhouette we're gonna get on the, once we rotate it?
it's going to change everything, right? Depends on the function, right? So if I do more and more cylinders, right, and I let the number of these go to infinity, right, then you actually get the solid. It's exactly the same thing we did when we were doing Riemann sums. We did rectangles, then we made them smaller and smaller and smaller until we got the area underneath. Here, we're creating a bunch of washers, finding a formula for each one, and then letting the number of them go to infinity. So, I mean, I don't know about you, but it's pretty badass shit right here. I mean, because there's nothing that you really can't find the volume of anymore. Like if you could come up with a function that, and imagine what it looks like drawn, like rotated, then there's really no limit to the geometric shape you can find a volume of. Now you still have to be able to do the integration, because look at what the integration is. Here's the formula right here. The volume of the entire solid would be pi. Now I pull pi out because pi is a constant. Integral from A to B, and I want you to look at it this way. This is your radius out, that's your outer radius squared, and that's your radius in, that's your inner radius squared. You know how we were doing top minus bottom, left, you know, right minus left? Now I'm going to be talking about outer radius, inner radius. All right. I think an example is in order. Yeah? Let's do an example. Have you ever wanted to know what would happen if you took, I know you've never wanted to know this, but imagine you have the sine curve, right? And imagine that you take just that first little arc of the sine. We call that the first arc of the sine function. So this is y equals sine x. I want us to look at this on the interval 0 to pi. All right, so that's the yellow part. I want to rotate this about the x-axis. And I want us to find the volume. So geometrically, it's very much this problem right here, isn't it? I mean, that does kind of look like the sine function. Would you all agree? I mean, that kind of looks like the first arc of sine, maybe a little bit. And so when we take this and we wrap it, you know, do a bunch of rectangles and get a bunch of them in there, we're basically creating like a football. It almost looks like a football, doesn't it? What's the volume of that? That's the question. All right. Y'all ready to do this? All right. So here's what I'm gonna do. I'm gonna cheat. I'm gonna grab this and copy it real quick. Move it down. I need to move it down a little bit because I'm about to do something that I highly recommend you do. Okay, what I'm gonna do first is I'm gonna draw an arbitrary rectangle inside of here. Okay. Then what I'm gonna do is I'm gonna slide that rectangle to the side, just directly over here. I'm just gonna slide it over here. Okay, so this point slid all the way over here. This point slid all the way over here. Now I don't want all those dots, but I just moved it over, right? Next thing I'm gonna do is I'm gonna draw my x-axis, which is touching the bottom of the thing, isn't it? It's touching the bottom here. The next thing I'm gonna do is I'm gonna draw the axis of rotation. So my axis of rotation is actually the x-axis, but I'm going to label it, and I'm gonna do like a curved arrow that curves around back to itself. So it looks almost like a little circle with two little arrows. That's letting everyone know that that's also my axis of rotation. Now, we know the formula looks like this. Integral a to b, oh, there's a pi out front. We know that it's the outer radius squared minus the inner radius squared dx. So I just need to know the outer radius. The outer radius, I'm going to type this because I want this burned into your brains. I got to be able to spell, type. The outer radius is the distance from axis of rotation to the outer edge of the rectangle. So on my picture here, my outer radius is the distance from the axis of rotation to the outer edge of the rectangle. So I'm talking about this distance right here. That right there is R out. Now, can you tell me what it is? Can you tell me what
F of x?
dictates that? Sorry?
Is it f of x?
It is. It's the function right here. It's the red part of the curve. That red curve, right, is what dictates how far I am away from the x-axis. And what is that function for us?
Sine x.
Sine x, right? So our R out is just sine x. Now the inner radius, I'll put it right here so we can keep it all on the screen. Inner radius is distance from axis rotation to inner edge of rectangle. So do y'all see what that is for us here? There's the inner edge of the rectangle, right? That bottom edge. how far is it away from the axis of rotation?
0.
0.
0. Always, right? It doesn't matter where this rectangle is in our picture. The bottom edge is always 0. The top edge is always sine x. Do you all agree? Okay, no matter where your rectangle is, it's always sine x is going to give you the outer radius, and then 0 is going to give you the inner radius.
So it's actually the same thing. Always 0, like it's a
For this
bottom
problem,
or
for
top.
this problem it is. I'm not going
Yeah.
to say that the inner radius is always 0. It's not.
Mhm.
Okay, so I think we can set up the integral. Do we know what a and b are?
Yes, 0 to pi.
0 to pi. Okay, the outer radius, we know what that is, right? It's sine. Trying to make this all fit on one page. It is sine x, but then squared, right? Don't forget to square it. Sine squared x minus the inner radius. I never put here r in, is just 0 always. So that's 0 squared. Hey, hey, hey. Check that out. Sine squared x. We've done that before, right? Power reducing formula. I'm going to do this one. I'm going to take this one the whole way. 0 to pi. Okay, I bring out a half and then 1 minus cosine 2x dx. Bring the 1/2 out. Integral 0 to pi of 1 minus cosine 2x. Ready for the antiderivative now? Antiderivative of that should be x minus 1/2 sine 2x evaluated from 0 to pi. Now, I don't need to change this, right? This sine 2x, I don't need to switch that over to 2 sine x cosine x. I don't need to do that because we never did trig sub, right? Like we can just plug in pi, get an answer, plug in 0, get an answer. So this is where I plug in my two things. So if I plug in pi, I get 1/2 pi minus, what is sine of 2 times pi?
1. No, 2.
Oh, sine of 2 pi. Go all the way around. Y coordinate,
0.
0. Okay, then we have 1/2 pi. Plug in 0 for x minus. Now again, plug 0 in here. 2 times 0 is 0, sine of 0 is 0, so that's just gone. So that whole thing is gone. And you just get 1/2 pi squared. It's a strange value, but that's what it is. All right.
Yeah, it's funny how you make everything in 2 minutes. It'll probably take me 15, 20 minutes to do all this.
Yeah. Well, it should, right? It's the first time you're seeing it, right? And putting this all together now.
I think it's more easier comparatively to like the others, integration and other topics. Like it's more conceptual based. Like it's easier to figure them out.
Yeah. Well, historically in a class like, Cal 2 class, historically students do better with chapter 7, because it is more visual. And so they do better with it. And it's just not as much kind of like grind to it. You just have to kind of make sure you understand the geometry, and then you're in business. So here, let's do this problem. I'm going to let you talk about this amongst yourselves. Prove the volume of a sphere is V equals, does anyone know the volume of the sphere?
4/3 pi r squared.
4/3 pi r squared?
Cubed, sorry.
Cubed, I think it's cubed. 4/3 pi r cubed. Double check that. It's on your formula sheets. I'm pretty sure it's cubed. I have these brain farts every once in a while where I can't remember. I'm not a big memorization person. So you're confusing the area part, but volume of sphere is 4/3 pi r cubed.
I think volume is always cubed.
Hmm?
The volume
No,
is
no, no.
always,
Your volume doesn't always have to have a cubed unit in there. I mean, your answer would have a cubed unit, like it'd be inches cubed or feet cubed or meters cubed.
yeah.
The unit would have to, but the formula doesn't have to.
Oh, okay.
All right, we're gonna do breakout rooms, if that's okay with everyone. I'm gonna let you all kind of talk amongst each other for a few minutes. Let me make sure. Okay, close all rooms, recreate rooms. There'll be 4 people per room, so let's see how this goes. What I want you to do in these rooms, don't go in there yet. What I want you to do is talk about the strategy, the approach, how you go about going after this. All right, I'll give you all, I don't know, 10 minutes. Enjoy. We're just gonna wait for everyone to get here. All right, we should all be back here now. So in the group, I went in and visited each group, and the closest that anyone got was the group room 1 with Brian, Cameron, and Celeste. So do one of y'all want to kind of explain what you had explained to me when I was in there? How you were approaching it?
So as I thought about it, you start off with like a half circle on a coordinate plane, and then you kind of rotate it out from there. But the problem we ran into was finding, a function for that half circle. And when we thought about it, we figured it out. It was just like, half the circumference of a circle. And then from there, we used, just did what we did for the previous question.
So did you get an answer?
No, I did something wrong.
Okay. So let's start off. Does anyone else from that group want to add anything to that?
I don't know if I did it right, but I got 64 pi squared over 3.
64 pi squared. So can you explain how you did it?
We just picked, we did a pi of the integral from 0 to 4, and it's just the size of that interval, and then I just did what we did earlier.
0 to 4.
Problem.
You said 0 to 4.
Mm-hmm.
Why did you do 0 to 4?
I don't know. It's just, I guess you could just really do it from any interval to find any size of a circle, right?
Yeah.
Mm-hmm. So you did it for a specific,
just
fixed radius.
Yeah, just very specific.
And what did you get as your answer?
64 pi squared over 3.
So that's pretty, that's pretty close. Now, what did you integrate? What was your integrand? What was your R out minus R in?
So I did pi of the integral 0 to 4 times pi r squared, because I just divided half the circumference of 2 pi r, which would be half of the circumference of the circle.
Okay, all right. That's the part I wanted to see what you did. All right. So let's stop right there. Let's make sure everyone's on board here. All right, first of all, a sphere of radius r has this volume, and we need to prove it. What we're talking about today is that you can take functions, and instead of looking at the area under the function, you can take that region and wrap it around the x-axis and get a volume. So what you have to first figure out is, how can I create a sphere from wrapping something around the x-axis? So that's what the room 1 did, that group that just talked. They said, why don't we take half a circle, which would be this half circle, and wrap it around the x-axis. If we do that, then we will have a sphere, won't we? But there are a few things that were not resolved correctly there, and that is, first, what is the actual function, right? What is that function that draws that half of the circle? So what you need to go back is do you remember when we proved that the area of a circle is pi r squared? I did that for you. When we did that, I first explained and reminded you that the equation of a circle is x squared plus y squared equals r squared. That's the equation of a circle that's centered at the origin, has a radius of r. Do you all remember that? Then I solved it for y, and we got plus or minus the square root of r squared minus x squared. And that we got by just moving the x squared over and then taking the square root and doing plus or minus. And then I threw away the negative one because I was telling you that to draw the circle, we only need the top half. So we're only going to take the positive answer. So this would be the function that would draw a circle of radius r, and it would draw the top half. Do you all agree with that? Yes? So what I'm going to do now is I'm going to ask you to consider this. Instead of taking the whole top half and wrapping it around the x-axis, is it okay with you if I just chop off the left half and rotate just the right half of it around and then just double that answer? Is that okay? Because if I wrap just that around the x-axis, we're going to have half a sphere. All right, we're going to get this shape, roughly, right? So let's consider this. I'm going to draw a rectangle. My rectangle looks like this. If I move that rectangle over here to the side, I have my x-axis, which is here. I have my axis of rotation, which is also here. And now I just have to determine what's my r out. And then my r in is down here. My r in is 0 because that rectangle touches the ground. What's r out?
Square root, the y.
Yeah, it's the top of that circle. So it's r out is that, right? There's only two other things I need in order to do this, and that's my limits of integration. So my rectangle is going to be sliding in here between where and where? What are my x restrictions?
0 and
2 pi.
2 pi.
No,
would
R.
you set
r. It's r, right? Isn't it just the radius of the circle? Which is r. We don't know what it is, but it's r, right? So my integral should look like this. Pi integral 0 to r of the outer radius squared minus the inner radius squared dx. Oh my goodness, life is great. Look at this. I'm squaring a square root. I like squaring square roots because all that I'm left with is r squared minus x squared. The 0 there goes away and all I have is that. Right? And now I'm going to just find the antiderivative of each of those. Now don't freak out because remember r is a constant, isn't it? R is the radius of the circle. So, oh, no more integral sign. So what is the antiderivative? Careful. What is the antiderivative of r squared?
1/3 r cubed.
No, r is not a variable. Our variable is x.
So r square x.
R squared x. Right? So r squared is a number. Maybe it's 100. Who knows what it is? The antiderivative of 100 would be 100x. So whatever the constant is with an x next to it is the antiderivative. Now this one is the 1/3 x cubed. And we're going to evaluate that from 0 to r. Right? Pi. Okay, I have to subtract two things here. First, let's plug in r for x, right? We're going to plug in r for x. So that gives us an r cubed minus 1/3 r cubed. And then when we plug in 0 for x, we get 0 minus 0. What's r cubed take away 1/3 r cubed?
2/3 r cubed.
2/3 r cubed. So our answer right now is 2/3 pi r cubed. What was our answer supposed to be?
4.
4.
Oh.
Oh, wait, we did half of it, didn't we?
Yes.
We did half of it, right? Remember, we had only done this half. So I just need to double this answer. So if I take this answer and multiply it times 2, we get it, right? 4/3 pi r cubed. There it is. Now that you've seen it, doesn't that seem like a pretty trivial result? I mean, it's, once you understand what the function is, and you can set up your integral, the actual integration is pretty straightforward. If you look back in our notes, when we did area, when I showed you, it was a while back, I showed you that the area, oh here, wow, what are the chances that I click right on it? This is when we did in class, I showed you that the area of a circle is pi r squared. We took half of this thing, and then when we did the integral, here was our integral. And we had to do trig sub on that integral. So we did trig sub, and when we finished all the trig sub and everything else, we got pi r squared. And we were like, yeah, we got pi r squared. Now we did a similar thing, except instead of just having the function here, we had function squared, outer radius squared minus inner radius squared, and that squaring of the square root made life great because we never needed trig sub. Interesting. All right, well, we just started to get into this section. We still have more to do because we have to be able to handle, what if our graph looks like this? And what if we want to take that region and wrap that region around the x-axis? Do you see we're going to have a problem? Because these aren't functions of x. So you can't do a rectangle right here. You can't do an r out, r in. So we're in trouble with that. So we have a lot to do in this section still. All right, there's still quite a bit, but for the in the meantime, make sure you get all your 7.1 homework done. Make sure you're up to speed on that. We'll come back and we'll hit 7.2, 7.3, and we just keep on plowing away. Any questions? Oh, wait, you wanted these notes, right? And then there was something else. I was going to show you on the calculator. Would you all like to see that?
Yes.
Okay. Sure.
Let me export this real quick.
So like the calculator would show us the graphing?
Yes.
Oh, shoot.
Okay, I'm going to send it in the chat if that's okay with you all. I'm going to send the file. Maybe. Today's notes are in the chat as a PDF file. All right, now I need to bring up my calculator here. Now this, for me to show you this is going to take me, another probably 10 minutes. So if you have the time, great. If you have to go ahead. All right, so here's what we're doing. I'm going to get a new page here. This is all right, so everyone should be familiar with the y equals. You have to know how to do that first, right? So the way y equals works on your graphing calculator is if you have a function f of x equals, let's just say x squared minus x plus 1, then of course you just type in there next to y1, you would type that in, right? And let's say we have another function, let's say g of x, and let's say that is sine x. So in y2, you would just do sine x. Now, here's the thing that you have to understand. Your calculator is simply just evaluating functions and plugging in points, right? So when you graph this, let's say when you graph this one, what your calculator is doing is it's making really like a table. And it's starting with some X values and then figuring out what Y is. So your calculator goes, oh, I'm going to let X be 0, plug that in here, and I get 1. And then it says, I'm going to let X be 1 and plug that in and I get 1. And it says, I'm going to let X be 2, and then it spits out a Y. So every time you plug in an X, it spits out a Y, right? All right, and it does that for both of those. So we just go in here and we type that in, right? Right, okay. I want you to look at this in a slightly different manner. All of these points, right, are just the points X got plugged in and then the function's value there got spit out, right? X got plugged in, the function's value got spit out. So this value here depended on that X, yes?
Yes.
Value depends on this X. I want you to just think of something completely different. I want you to think of an ordered pair where the X coordinate depends on some value T, and the Y value also depends on T. For example, if I told you that X of T was just T, and I told you that Y of T was T squared minus T plus 1. Does that look familiar to you? X squared minus X plus 1. I wonder what a table would look like here. What would my X be and what would my Y be for different values of T? So let's let T be 0. Let's let T be 0. What would we get for X?
0.
0. And what would we get for Y?
1.
1. Okay. What if I let T be 1? Well, then X is
1 and 2.
What is it? 1 and 1, right?
2.
Plug 1
Oh,
in
yeah.
here, right? We get 1. If we plug in 2, what do we get?
2 and 2.
And then
4,
3?
4,
3.
3. Yeah, 3.
Do you see that those are the same values we were getting up here? You see that this table is the same as this table.
Mm-hmm.
And the reason why it's the same is because if we look at this as an ordered pair, the X value is just T and the Y value is this, T squared minus T plus 1. So this value actually depends on that value T. So here's what I want you to do. I'll get to my whole point here. I want you on your calculator to go hit mode. Okay. And then when you scroll down, you're going to see option for func, which is function, pair, which stands for parametric, pole, which stands for polar, and then SEQ, which stands for sequence. We want to select pair, which is parametric, and then hit enter. Okay. Now, once you've done that, go back to your Y equals. And you're going to see something different now. What you're going to see, instead of Y1, Y2, you're going to see X1, Y1. Then you're going to see X2, Y2. Then you're going to see X3, Y3. And so the way this works is you put everything in as a pair. So if I wanted to graph this parabola right here, what I would do is I would let X1 be T. So you have to use that key. You see the key that says X, T, theta, N? You're just going to hit that button and it's going to throw a T in there. Okay. And then my Y value, I want that to be the parabola, T squared minus T plus 1. So we're going to go down, hit enter. Next one, we're going to go T squared minus T. Oh, shit. Clear. T squared minus T plus 1. Then hit enter. And now I would like for you to hit graph. And it's only going to draw one side of it. It's only going to draw one side of that parabola. And the reason why is because the calculator, when it's programmed, when it comes from the factory, it restricts the value of T. And so we have to go to window and it says here what the T minimum and the T max is. Just change that to like -10 to 10. The default setting for the calculator is 0 to 2 pi. That's what the default setting is for parametric mode. And now if you do that and you hit graph, you're going to get the whole parabola. Okay? Now, check this. This is the part that's cool. Let's say that we want to do this instead. Okay, now this is a function of y, isn't it? Not a function of x. Well, I can use the parametric mode by doing this. I'm going to let the y be t this time, and I'm going to make the x be the function with my y's replaced with t's. You see how we're just like switching places? Go back to y equals, leave this one in here and move down to the next one. To x2, put t squared minus t plus 1, and then in the y2 just put t and then graph. And you're going to get the parabola going the other way. Does that kind of make sense?
Mine doesn't intersect. I don't know why.
You may have typed it in wrong.
I typed it.
Yeah, I didn't get anything
Oh,
either.
yeah. Yeah. Oh, yeah. Because I typed in t squared plus t plus
Oh, yeah,
1. It was
it's
t
minus
squared
t.
minus t.
Yeah. So now let's go back to y equals. Let's just clear all those out. Just clear all this out. So here's what I'm saying. Every function that you've ever had in your life that you've ever looked at. Let's say you take f of x equals, let's say you wanted to graph this. Standard function. You can stay in parametric mode on your calculator. It's just what you're going to do is you're going to let the x1 be the t, and you're going to let the y1 be that function, but t's instead of x's. That will graph that function. Now, if you want to do a function of y,
What does t stands for here?
t is what we call a parameter. It's really like, you know, normally when you have an x and y axes, when you graph something, the input is x and the output is y, right? So you're visualizing, you can see the input in the graph. With parametric equations, or parametric functions, equations, t is the parameter. It's like a clock running in the background. And so it's drawing as time goes on. And we're using that, but the fact that we're not changing what x is just t. I mean, just think about that. If x is t, then isn't this just x times sine x?
Yes.
If x is t,
But I
isn't
was
it, right?
yes.
And then let's do this one. What if we wanted to graph, remember when we were asking earlier, Cameron asked, what does sine y look like, right? Well, in our calculator, we would just do, which one of these would be t? This is a function of y, so we let the y1 be t, we let the x1 be sine t. And again, the idea here is that if y is t, then that's really a y right there, and that's really sine y then. So I'm gonna go up there and graph that. If you're understanding this, great. If you're not, you know, don't worry about it. It's not the end of the world.
The reason I'm more interested because I bought this calculator. Now I don't want to know what it does.
Yeah. So there it is. There's the graph.
So that was the y1 was t here, right?
Yes.
And
So
that was t.
if you're going to do a traditional function, like a traditional function, then you're just going to let the x be t, and then you let the y be the function with the t's, the x's replaced with t's. If you have it the other way around, and it's a function of y, you're going to let the y be the t and let the x be the function with the y's replaced with t's. I hope that makes sense. But in theory now, you could graph, you don't ever have to change your mode on your calculator. You could just stay there for the rest of forever if you wanted to.
So this,
You
the
don't need
what
parametric.
was, yeah, parametric.
So these are called parametric equations. Come here. These are called parametric equations. And the beauty of a parametric equation, I'll show you the beauty of a parametric equation if you have a moment. Go back to y equals. I'd like for you to type in, clear that out. I'd like for you to type in cosine t. And then for the y, don't type in t, type in sine t. And graph it, and you'll see the power of parametric equations. Do you see what it draws?
A circle?
It draws a circle. And the unique thing about this circle is that we drew it with a function. Because
So
for every input, for every t that goes in, we have exactly one output. But our output is an ordered pair. So we're getting way beyond anything we need to in this class. I mean, right now, essentially what we're doing is this. Every function that you've been dealing with in your life, every function you've dealt with has always taken a number in and has spit a number out. That's what's happened. You take a number in, send it through the function, number comes out. Parametric equations work like this. They're functions that take a number in. The number it's taking in is t. But it's not spitting out a number. It's spitting out an ordered pair. It's spitting out a pair of numbers. A pair of numbers lives in two-dimensional space. So it's a function that goes from the real numbers into two-dimensional space. And so for every input, as I plug in values of t, it's drawing me the circle, and we don't have vertical line test and horizontal line test anymore. It's gone. It's no, you don't have to worry about it. Go back.
So I
in
can
here.
use my calculator here in terms of 7.1 and 2 to figure out my
Graphs.
graph.
If you're having trouble with the graphs, you can use it.
Oh, wow.
I'm going to change it. I'm going to go t cosine t. And on the next one, I'm going to go t sine t. And this one is pretty cool. T times sine t. And graph. All right. What you can't see is that this just drew a spiral. It's drawing a spiral. Which is definitely, that would fail the vertical and horizontal line tests, but I'm telling you, it is still a function. Now, why this is important later is because in the real world, we have objects that move around, right? Like think about if you're tracking, let's say you're tracking a vehicle. Let's say we're looking from the top down. You're tracking a vehicle that's driving around, right? So you're tracking it. I can't do any calculus to this now because I can't look at that as a function, right? Because if I start to draw an X and Y axes on this, it's not a function. It fails the vertical line test, fails the horizontal line test also. So there's no way to really do any calculus with that path. But if we look at it from the parametric point of view, it is a function and we can do calculus. That's what Cal 3 is about.
For this input, for the spiral, what did you enter?
T
Was it
cosine t times t times t sine t. But what makes it even better is then you take this in Cal 3 into three-dimensional space. So now what you have is some object moving around in three-dimensional space, and then you can start doing calculus within there. So you can talk about, okay, if you have an object moving along this curve, moving in this direction, then right there, at that instant, what is its velocity? Velocity is a vector. So that would give you both the speed and the direction. But you can't do any of that until you have dealt with the idea of parametric equations, which gets us around the whole vertical horizontal line test. It opens up a whole new world to us. All right, I'm going beyond what I need to. Now you have a way of graphing these things, if you need help, all right? Anything else? I gotta run.
No, thank you so much.
Okay.
Thank you very much.
Good weekend.
You too.
Thanks.
Thank you.
This weekend.